let's go ahead and get started here. My iPad is not dead, so that's a good start to the day. So we're just gonna keep going with these, crank these things out, do an example with this polar and cylindrical coordinates, and then start this relative motion stuff. We have exam in 2 Fridays from now, not this coming Friday, not the following Friday, but the next one. I think the 29th, I think is what it is. Another little note, I will not be here on Monday. So I will pre-record a lecture and post that. My wife's grandmother passed away, and so we have a funeral in Billings for on next Monday. Her husband of 75 years died like 3 months ago. It's pretty crazy how that happens. Died. You've heard of that before, and actually it actually happened in this case. So pretty crazy. Anyways, so I'll put an announcement on D2L as a reminder as well. Okay, so polar and cylindrical coordinates. What are they? How did they come about? Right, we set up this new coordinate system. You got some point of origin, and then you've got a position vector pointed to a particle, right, from the origin. And then if you keep going, if you follow that same path that R is going in the ER, that would be the ER direction. It's in the direction that position vector is at. And then E theta points in the direction of increasing theta. So if theta is getting bigger, it points in that direction, okay? Gets confused with normal tangent often. Normal tangent, we have this guy going this direction and one pointed back to the instantaneous center of curvature. So that one's different, right? So this is slightly different. Actually, it's quite a bit different. And I'll explain the difference and why you would use one over the other in a little bit. Okay, so that was that. When we define what the position is, right? It's R in the ER direction. When you take the derivative of that with respect to time, you use the product rule, and then you end up with a couple of different terms. You have your velocity has 2 terms. It has R dot getting bigger, right? This R dot getting bigger, and it has an R omega term with it because there's some velocity associated with it moving. Yes?
Is the theta in radians or degrees?
Everything's in radians. Yep, everything's in radians. That's a great question. Right? Everything's got to be in radians for this stuff to work. Okay. So then when you do that, so that's what our velocity is. So our velocity actually has 2 terms in it. It's got the R getting bigger, and it has an R omega term as well because the theta is changing, right? So then we take the derivative of our velocity, right? Now we take the derivative of velocity, it blows up on us, right? You get all sorts of terms associated with it because of the product rule. And then we converge upon this right here. Acceleration is this. It's R double dot minus R omega squared plus R alpha plus 2 R dot omega in the E theta direction. So you have 2 components, the ER and the E theta, but then you have multiple terms inside of each one, right? We discussed each one of these things, the radial acceleration, the centripetal acceleration, tangential acceleration, and then there's this thing called the Coriolis. On Friday, we'll look at a video of some Coriolis stuff. But that has to do, when you talk about a merry-go-round, that's always the best thing. I always like to think of that because it has all of these terms in there. Like if you're on a merry-go-round and start walking towards the outside or sprinting towards the outside or something like that, all of these terms become active and they actually mean something in there. Okay, so that's kind of where we left off last time. So a special case is if something's actually traveling directly like in a circle, okay? General terms, you don't have to travel in a circle. So if we were looking at this, if you had a merry-go-round and a person was walking towards the outside, they're not traveling in a circle, right? If you imagine what they're doing is they're walking out, they're actually doing this, right? They're traveling in a spiral. If you think about their actual position as they're walking out, they're not in a circle. And that right there is probably the best way to discuss the difference between normal tangent and polar coordinates. It would be very hard for normal tangent coordinate system to handle a motion like this, right? It would be very difficult, right? But if it was a fixed position, right? If I was just set in one place on this thing and it was traveling around in a circle, that's a different story. Actually, the 2 end up being exactly the same, okay? And so the other one, they also call the normal tangent coordinate system the path coordinate system. And if you're trying to track that path, you would have to have an equation for that path as it went around, which would be a spiral. So it's more difficult to do that way. And so that would be an example. It would be when you would use this polar cylindrical coordinates. Okay, so if we're talking about something traveling directly in a circle, so a fixed R, right? So if you're on that merry-go-round and you're not moving and just standing in one location, let's look at the equations for that. All right, in this particular case, R dot would be 0, right? For these equations here. Let me get this all squared away here. Make sure I don't miss anything. Yep. R dot would be equal to 0. Right? If you're in a fixed location, travel in a circle, again, your ER is going to be coming out this way. E theta would be going this way. All right, in this case, since you're not moving in and out, R ends up being equal to 0. Sorry, just R, not the R vector. R is equal to 0. And then also, sorry, R is not equal to 0. R dot is equal to 0. It's one of those days. I wasn't done yet. I wasn't done speaking yet. The velocity in that direction would be equal to 0. R isn't 0. It actually has a radius associated with it, but your change of R is equal to 0. And then also your R double dot is equal to 0 as well, right? If you have no velocity, no acceleration outward. And so you just take that and you put it into this above, right? You take these two things and then force those being equal to 0, right? And then all you get is these equations right here. Right? Your velocity becomes R omega in the E theta. You're going to get used to seeing this a lot throughout the semester. If you want the velocity of something traveling in a circle, then you just take the radius, you multiply it by omega, right? The radius, and whatever unit you're using, that omega in radians, so that it turns out to be the right radians per second, so that it ends up being the right units as you go out, right? And so that's your velocity, just as R times omega. We saw that before. That's exactly what we found in the normal tangent coordinate system, right? We found that the velocity in the tangent direction was just R times omega, okay? And then the acceleration term becomes this, minus R omega squared in the ER direction, plus R alpha in the E theta direction. Again, we found that for the normal tangent. So they converge on each other. The polar cylindrical coordinate system and the normal tangent become the same thing, almost slightly different. And the difference is that R omega squared term is negative in this coordinate system, and it was positive when we were doing normal tangent. And the reason for that, in normal tangent coordinate system, you'd have tangent going like this, and you're actually, your EN hat would be pointed back towards the middle, and so it had a positive acceleration term for the R omega squared. And this is a negative because ER is going out, and then your acceleration term's going in, so you end up with that negative out front there. So just make note of that. So if you're doing a problem and it is a circle, right? You can use either coordinate system. You can use normal tangent or polar coordinates. Your choice, right? Okay. Cylindrical coordinates, right? So if you had cylindrical coordinates, that's just basically adding a z component to it, right? We're turning this guy into a cylinder. We're adding a distance into the board, right? And so that's how you do these 3D problems. You would do it in cylindrical coordinates. What you do is you just add in a z component. Right? You can see right here, we've just added in, your position is going to have R in the ER direction, and then just add in a Z in the K direction. That's all we do. Same thing with velocities, right? This is our velocity term right here that we just derived, and then we just add in a Z term. And so that's going to be the derivative, how Z is changing with respect to time. That's the Z dot. And then our acceleration, right? These are our two acceleration components in the ER and E theta direction, and we just add on to it a Z double dot, right? And so there's a couple of your homework problems have this component to it, right? You just add in a Z component. And it doesn't really affect anything besides just adding in those things. Okay. We also, one more bookkeeping thing before we do an example, we also have a conversion between the two, right? When you solve these problems, you figure out what ER and E theta are, the velocity in the ER direction and the acceleration in the ER and the velocity and acceleration in the E theta direction. but we really don't like. We'll see an example in a second where where you'd want to do this, but like it could be my acceleration, my velocity could be in this, could be over here, it could be over here, it could be over here, it could be over here. These things change with time. It could be wherever you're at. It could be all over the map here. And that's okay, because usually what we're after, like, what kind of forces does the passenger feel from the car as it's going around the corner? I don't really care where it's at in the global world. I just kind of care how much is pushing back against me as I go around the corner. So usually it's okay to not know exactly where those coordinates are, unless you're trying to compare it to something else. And when you start trying to compare it to something else, you have to get everything in the same coordinate system. And then when you do that, you got to use one of these conversions, right? And you derive these the same way we did in normal tangent as well. And I'm just going to give them to you here. Okay, that's it. So basically, the way you convert between it, anywhere you see an E theta, you substitute this stuff in, and everywhere you see an ER, you substitute this stuff in, and then that'll convert everything to Cartesian coordinate system. Okay. This is a really boring example. We already talked about this a lot, but it takes like 2 lines here. So it says, given a merry-go-round is spinning with a constant omega, you start to walk to the outside with a constant r dot. So we're on this thing somewhere, and we start to walk to the outside with a constant r dot. Okay. And it says, what is A? So we just write down the equation for A. R double dot minus R omega squared in the ER direction plus R alpha plus 2R dot omega in the E theta direction. Okay? In the problem statement, it says omega is constant. Right? If omega is constant, what does it tell us about alpha? 0, right? Alpha is the time rate of change of the velocity, angular velocity, so alpha is going to be equal to 0. And then also r dot is a constant. R dot. Right? If r dot is constant, it tells us that r double dot is 0. Right? If r dot is constant, then r double dot is equal to 0. And so up above, r double dot 0, r alpha 0, and so then we're just left with acceleration is negative r omega squared in the ER direction plus 2r dot omega in the E theta direction. Done. Okay. A lot of these problems are just kind of identifying what is what in this acceleration equation, right? What r double dot is, what r dot is, things like that. Yep. As you note too, we're nearing the end of this set of notes. So then sometime in the next couple of lectures, you might want to print out the next set if you're using the skeleton notes. Okay. A little more interesting one. Okay. So this is a little block that's inside this little slot. This came out of your book, or a book somewhere. And it's got an omega. This thing's rotating around. And this little block can move inside that slot. Okay? And it actually gives us the velocity as a function of time inside that slot, what r dot is. That's the rate in which, that's the speed in which this guy is moving radially outward. Okay? The platform rotates at a constant theta dot, right? Or omega equal to 6. The block starts from rest at the center, so it starts right here. And it says find the magnitude of the velocity and acceleration at t equals 1 second. So this is a little bit more interesting because now we got acceleration a function, in this case, velocity is a function of time. So there's a little bit more going on. Okay? So we'll just start out, I always start these problems out where I just say, let's write down the velocity equation for polar coordinates. This one's going to work better for polar coordinates than normal tangent, because again, think of the path that this guy's taking. It's doing a spiral as it moves out, and so that'd be really hard for normal tangent to handle. This guy can handle it better. All right, sorry. Polar coordinates can handle this better. Okay, so the velocity in polar coordinates is going to be r dot in the ER direction plus r omega in the E theta direction. My acceleration, I'm just going to write that down to know what we're after here. Again, is r double dot minus r omega squared in the ER direction plus r alpha plus 2 r dot omega in the E theta. Okay? That's all of my terms there. We know that r dot is given to us as being 4t meters per second. Then r double dot is just going to be 4 meters per second squared. Did that derivative in my head right there. I was proud of myself when I do that. I would honestly probably pull out a calculator usually, but this time I got this. Right? Omega, the same as theta dot, just to make it clear that those are the same things. They gave us that. Theta dot is 6 rads per second. And so then alpha is equal to 0. Just some kind of bookkeeping stuff just so we know what those values are. Okay? And so I should just be able to take these terms, right, and then just substitute them up above. Where the problems there are actually we're going to run into right away is even just for velocity, right? I know what you're trying to find the velocity at 1 second. So I could just plug in 1 second into this t and then take that and put it right there. Perfect. Yeah, I got that term. Over here, though, I got omega, right? Omega is 6 radians per second, so I could substitute that term in. What I don't know, though, is what the radius is, right? They didn't tell us what the radius is going to be at 1 second. I have to find what the radius is at 1 second, right? And I do that, by integrating, right? They give me that. It goes back to this is a kind of a 1D problem where I have a constant acceleration and I have to figure out what position is based off of that. So you kind of go back to the stuff we did the first week of class to do that, okay? So just say we need R at t equals 1 second. I need that before I can keep going. Okay, so what I do there, I go with my r dot is equal to 4t, right? This is equal to dr dt, right? R dot means that, so you put the t's on the same side as stuff as the other t's, so you get dr is equal to 4t dt. I integrate. This is going from 0 to r. This is going from 0 to 1 second. Okay. You could not put in the 1 second. You could put a t there, and then what you would get is r as a function of time, and then you could substitute the t in later. I'm just going to throw it in here because I know that it's going to that. So then this becomes, or your solution to this, you get r equal to 2 meters at t equals 1 second. So a little side step along the way to determine what my position is. I need that r. It goes into the r omega squared term. It also goes into the r dot omega term and the r omega term. So you need those at that radius. Okay. Like I said, I could have put a t right there and solved for r as a function of t and then put t in later, but I just did the definite integral there. Okay? So now we're ready to substitute more in. My velocity is equal to I'll write it all down again. R dot in the ER direction plus R omega in the E theta direction. And then we just substitute terms in there. This is going to be the velocity is equal to R dot so R dot is 4 times T, but we're doing this at 1 second, so it's 4 times 1 in the ER direction, plus the radius we just found is going to be 2, and then our omega that they gave us is 6. And that's all in the E theta direction. So then my answer is, I'm going to do all this math in my head here. 4 times 1 is 4 in our direction. 2 times 6 is 12. Did it all by myself. And then the units on this. There are our units here. Meters per second. Okay. The problem statement may have asked for the magnitude. To get the magnitude of that, you do the square root of the sum of the squares of those terms. Okay. So not bad. Once you kind of get those values, you just kind of substitute them into the big equation. Okay. Now, last thing we got to do is the acceleration. Acceleration term. We got r double dot minus r omega squared in the ER direction plus r alpha plus 2r dot omega in the E theta direction. And we got all those terms. You just substitute all those terms in. R double dot we determined to be 4 minus the radius, which is 2, which is omega, which is 6 in your direction, plus r times alpha. Alpha was 0, plus 2 r dot was 4 times 1 second, times omega, which is 6. All that in the E theta direction. I guess technically we know what this r is too. I mean, it gets multiplied by 0, so it doesn't affect the answer, but that r is 2. We figured that before. And what you get is my acceleration vector is going to be negative 68 in the ER direction plus 48 in the E theta direction, meters per second squared. And again, if I think the problem statement did ask for the magnitude, and so you do the square root of the sum of the squares of those values there. Cool. Not bad, right? It looks scary at first, but it's not that scary. The only thing that was kind of scary there is like, oh God, how do I get r? And then we had to do this integral, right? Integrals are scary. Okay. Okay. I will point out too, as you're well aware, I have terrible handwriting. But then my final product, I think, turns out okay. Right? I am structured, I am organized. So if you have bad handwriting, it's okay. You can still do it. I'm a doctor and I have bad handwriting, right? But you just keep it nice and tight and just really organized as you go through, and that goes a long ways. Honestly, as part of being an engineer is being that. It's just being tight and organized on how we, present our answers and highlighting them. And then if I'm the one that's grading them, it's really easy to grade if it's nice and organized. If it's not organized, then I get angry and in a bad mood. It's that I take it out on you while I'm grading. Just try to keep it clean, as clean as possible. Okay. Next topic is relative motion. So that's kind of all for all that's our core. We're in the middle of kinematics right now. We haven't talked about forces yet. That's the next step. That's kinetics. We're still in the geometry of motion, the very first thing that we're doing in this class. The last subject in kinematics is this idea of relative motion. This is going to play out really big in rigid body stuff, so we'll get to that, where we're headed in a couple of weeks. We'll use this a lot, okay? We've briefly discussed this before, right? Like we were talking about reference frames. Like if I was talking about the velocity of this Frisbee up here, how fast is that Frisbee going relative to the plane is significantly different than how fast that Frisbee is going relative to the Earth, okay? But there's a way that we can calculate how fast that velocity is going based off of those other two velocities, right? If I know the velocity of the plane and I know the velocity of the Frisbee relative to the plane, I can calculate how fast that Frisbee is going overall in the absolute, okay? So that's what this is all about, is how do I calculate the velocity of that Frisbee systematically based off of the velocity of the plane and the velocity of the Frisbee relative to the plane. Okay, so what we do is we just go back to vector math. All this stuff is based off of vector math. So if I've got 2 points in a coordinate system, right, A and B, I've got a position vector that points at A. Okay, we'll call this RA hat. RA bar, I guess. That is the position of A relative to the origin. And then I can go the position of B, call that RB. Okay, and that's the position of B. And then I can get to the velocity of A from B with this vector. And we're going to call this is RA as seen from B. That's whenever I write it like that, the A/B, that's what I always say. In my mind, I'm saying, all right, this is the position of A as seen from B. I always do that. That always kind of keeps it a little bit cleaner in my mind that what's happening. Or you could say the velocity of, or the position of A relative to B, right? If you want to do it that way. Okay, I always say as seen from, which is a little bit easier in my puny brain. Okay, so we can do that. That's just vector math. You guys learned that in math class. If you want to get if you want to get from one point to another point, you just add the two together and they're equivalent. So if I say if I wanted what RA is, I could just RA is RA, or I can get to RA by going RB plus RA is seen from B. I could do that, and you end up in the exact same position, and that's what this is all about. It's all based fundamentally off of that vector math that you see right there. Okay, so it's kind of these terms. I'll say this is really big. Oh, no, it's not. Positions of A and B relative to the origin. Or sometimes it's called the absolute position. Kind of defining some of these terms. And like I said before, this is the position of A as seen from B. Or relative to B. Again, I always say as seen from B. Okay? And then if I want the position of A, like I said, it's just vector math, and I could just say, well, I'm going to take the position of B, and I'm going to add on to it the position of A as seen from B, and it gets me to A. Okay? Just vector math. Now, for velocities, I would just take what you do is you just take the derivative of this, and then you end up at this right here. Right? It just carries over. If I want the velocity of position A, or point A, or particle A, so if A is moving, and I know the velocity of point B, and I know the velocity of A is seen from B, I just add those two together, because the velocity is also a vector. And so I just do vector math there as well. Right? So that's how we do the velocities. Okay? Same thing with the accelerations, take the derivative of that. If I want the acceleration of A, I'll just say that's acceleration of B plus the acceleration of A is seen from B. Okay? Just simple as that. The book kind of goes through full derivations of these, but I don't think it's that big of a deal. It's just vector addition, right? So back in the plane example up above, if I was saying, well, what is the velocity of that Frisbee? Right? And just, you would say that, say, well, the V Frisbee, the overall Frisbee speed, we'll call it VF, is equal to the velocity of the plane plus the velocity of the Frisbee as seen from the plane. Right? And that just makes sense. Right? Like that's just common sense, right? Oh, if I want the overall but it works if I apply this methodology up here, these velocity thing, right? If you apply that, then it goes to what your logic would say would happen, right? If I want the velocity of the Frisbee, I just take the velocity of the plane plus the velocity of the Frisbee as seen from the plane, and it'll give my total velocity, right? Okay, great. I think I post this. I don't know if I did post this. Be careful of this. If I haven't posted it yet, I'm going to. If you, I gotta make this really clear. What I've written here is the right answer. Okay, this is the right answer. The back of the book and the solutions manual, if you have the solution, has the wrong answer in it. The wrong answer, I think it has both of these being positive or both of them being negative, and that's not right. Okay, I hate when the solutions manual in the back of the book does that because it really throws you off. Because here you're trying to learn, and then you're like, oh my God, I keep getting the wrong answer. What have I done wrong? And you go back and analyze it a bunch of stuff, and straight up, the answer in the back of the book is wrong. Okay, the right answer is what I have right there. That's added confusion before too. It's like the wrong answer is this. I should be more clear about that. Okay. What are we doing here? Oh, we got a lot. Look at all the time we have. Okay. An airplane is pointed due north with an airspeed of 560 miles per hour. Wind is 60 miles per hour at 30 degrees as shown. We haven't shown it yet. Okay. What is the ground speed and course of this airplane? Okay. And so let's draw the wind. I haven't drawn the wind yet. So this is the X and Y direction. And we've got wind doing this, 30 degrees. Okay, that's what the wind is doing. Right, and my airplane's over here. An airplane. That's a pretty good airplane. I used to be like really self-conscious when I would get in front of big classes like this, and then I would draw, and I was like, oh my God, they're gonna see how bad of a drawer I am. But then I walked around and looked at all your drawings, and you guys suck at drawing too. Okay, there's some of you that are good. There's some of you that are good, but then most of you are not. So I go back and look. I was like, oh yeah, look at that shit. I do just as good as you do. So now I'm okay with it. Now I just accept it. Right? My brain doesn't work that way. And in fact, the harder I try to draw something nice, the worse it becomes, right? That's a true statement. Same thing with my handwriting. The more I concentrate on my handwriting, the worse it becomes. And the other thing that happens too, that while I talk, my handwriting becomes worse while I'm talking while I'm writing. And most of the time, I'm in like the one profession where you have to do that, where you have to write and talk at the same time. And I can't handle it. My brain can't handle it. It just doesn't work. So it's pointed due north, right? And you can see what's happening, right? That it's pointed due north. It has a certain ground velocity, and then as it's going that way, the air is moving, so it's just traveling to the side. So it's actually not traveling directly north. It actually is. It's got a little bit of a side push to it because the air that the airplane is in is moving to the side. Okay. And then its airspeed is 560 miles per hour. So and what I mean by that, its velocity relative to the air is 560 miles per hour. And someone told me once, I don't know if anybody's any pilots in here, but an airplane has like a little sensor, like a little cone that can measure the velocity of the plane relative to the air around it, and so that's how it gets that airspeed. Nowadays, there's like GPS that has the overall location, relative. But back in the day, they just used to. I'm sure they still have velocity meters in there as well, little airspeed meters inside the airplane as well. Okay, so it's doing that. So what it's asking us is how fast is it actually going, and which direction is it actually moving? Okay, that's what it's asking, and this is all a relative thing, right? And so the equation that we had for velocity was VA was equal to the velocity of B plus the velocity of A as seen from B, right? So in this particular problem, we want the velocity of the plane, the overall velocity of the plane, relative to the origin, or relative to the ground, is going to be the velocity of the wind plus the velocity of the plane as seen from the wind, right? So if I want the whole thing, I got to go the velocity of the wind plus the velocity of the plane as seen from the wind, and it'll give me the total velocity of the plane. Okay? So let's write down some of these terms. The velocity of the plane as seen from the wind, that is equal to 560 in the j direction. Okay? It's pointed directly due north. It's in the j direction, and it's going to be 560 miles per hour. Okay. The velocity of the wind, we're going to break it into its x and y components. It's going to be, the magnitude is 60, and then it's going to be cosine 30 in the I direction plus sine 30 in the j direction. Okay, all I did there is I just broke this thing into its two components. Right, the wind's going to have an x component and a y component. Right, the x component is going to be cosine 30 in the I direction, and then the y component is just going to be sine 30 in the j direction. Right? So there's our vector for our wind. So the overall is just going to be v wind plus v plane as seen from wind. Okay, let me say that. The velocity of the plane is equal to, let's say v wind, which is 60 times cosine 30 in the I direction plus sine 30 in the j direction plus, that's all v wind, plus 560 in the j direction. And if you carry out all that math, we get 51.96 in the I direction plus 590 in the j direction miles per hour. Right, that's it in vector form. Right? And what it asks us is what the ground speed and course is. Not that we're aviators here, but the ground speed and course is the magnitude of the right. This tells us everything we need to know. It's right going 590 north, and it's got a small 51.96 horizontal component. But that's not really if you're, I guess, in aviation, they have ground speed, so that'll be the magnitude of this. And then the course is how many degrees off north it's traveling. And so we'll finish it off like that. So say v plane ground speed is equal to the magnitude of v plane which ends up being 592.3 miles per hour. okay? And then this is if you draw this vector out, we got 590 in the J direction, and then we've got a small component. This is 51.96, and that's the degrees off north. This is the theta that we're after. That's the course, and that's going to be equal to the tangent, inverse tangent of 51.96 over 590. And so it's 5 degrees. Just to finish that off. There's that guy. Yep. Yeah, these aren't bad problems. That one's not bad, right? Let's look at this one. The next one. It gets a little more intense. I don't know if we'll have time to finish this one. I'll post this solution after class. We'll start it right now, right? So all the stuff at this point, and then even more after we finish this, you'll be set to do the homework. You have everything you need to finish the homework up this week. Okay. So the way this problem works, oh, I got that thing moved. Let's take a minute to describe these things here. All right, so this thing is, we have two cars, right? Two cars are traveling around at a constant speed around circular tracks as shown. Find the velocity of B as seen from A and the acceleration of B as seen from A at the positions shown, okay? So I have, this guy's traveling around at a certain speed, and then there's another car here traveling around at a different speed. They're on two different tracks, right? And so this is a culmination. This is the one that I've been telling you about. If I want to get acceleration of A is seen from B and B is seen from A, I have to have them in the same coordinate system, right? But then this is something traveling around in a circle, so it's easier to solve in polar coordinates. So in this one, what we're going to do is we're going to solve this thing in polar coordinates first and determine what the velocity and acceleration are of each A and B in polar coordinates. And then we have to go put things into Cartesian coordinates, and once you get them in Cartesian coordinates, then you can compare to figure out what the acceleration of B and A are relative to each other, right? And so this is going to be a case where we actually do care about what the exact velocity is at that point, besides just what they are relative to the polar coordinates. Okay. Make sure that everything's in here. For some reason, I'm losing some of my variables. VA is 36 feet per second. VB is 45 feet per second. It's right at 25 degrees right there. RA and RB are 1200. And so our coordinates are, just to make sure that we are on the same page here, we've got this guy right here. Right. This is going to be an E theta direction, and this is going to be an ER direction. And then we have another coordinate down here. This is going to be ER. And then my E theta is going to be going like this. Ooh, made it curved. And so when we get our answers in terms of ER and E theta, there's a little foreshadowing. Note that ER and E theta don't line up, or sorry, ER and ER for the two ones don't add up, so you can't just add them together, right? And then E thetas don't line up either. They're pointed in different directions. Okay. Okay. Just real quick. So one thing here, if I have the velocity of B, this is just right in our equations from before, what we just derived for relative motion. VB is equal to VA plus velocity of B is seen from A, right? So that's the equations that we kind of derived before. If I want the velocity of a certain point, I think the velocity of the other point and then I add on to it the velocity of that point relative to A, okay? And that would get me there. If I'm after velocity of B is seen from A, you just kind of flip this thing on its head, right? And then you say, well, the velocity of B as seen from A is equal to the velocity of B. Velocity, hold on. Minus velocity of A. Okay. So because the problem statement asks us that, right? Where's the velocity of B is seen from A? And so I need to figure out what the velocity of B is, and I subtract off of it the velocity of A. Same thing would be the case for acceleration. If I want acceleration of B is seen from A, that's just going to be the acceleration of B minus the acceleration of A. So make sure that is what we're after. Yeah, B is seen from A, yep. So this is what we got to do. So you can kind of, again, when you're solving these problems, it's nice to just kind of lay out like what it is that I'm going to do. This is what I want to do, right? So to do this, I just have to figure out what the velocity of B is, and I have to figure out what the velocity of A is. Acceleration of B and acceleration of A. And once I get those, then I subtract them from each other. But to do this subtraction, to do this right here, they have to be in the same coordinate system, right? I can't do that if they're, my ER is pointed that way, my other ER is pointed that way. I can't subtract them off of each other because they're in the wrong coordinate systems. So that's why we have to get them back into Cartesian coordinates before we do that addition and subtraction. But right now, though, let's do the velocity of A. Car A, right? I think it's easiest to do these things in polar because we have these centripetal accelerations, or you can do normal tangent because it is a circle that is traveling in. Velocity of A is going to be r omega in the E theta direction, or it's the velocity of A in the E theta direction. Right. And they give us the velocity of A, which is just 36 feet per second. Right, you can do it r times omega, or you can do the tangential velocity in there. Either one, those are interchangeable, r omega or the velocity. They happen to give us the velocity. They say it's 36, so we put in a 36 there. Okay, acceleration of A. That's going to be equal to r alpha minus, there's a couple ways, it'd be r omega squared in the ER. This is an E theta. Okay. It's constant velocity, so that guy's 0. There's no acceleration there. And then this r omega squared can also be written in terms of velocity, which is VA squared over r. I'm kind of using those things interchangeably a little bit, right? R omega squared or V squared over r, both of those things do the same thing. You can get at the same point. I could calculate what omega is. That'd be V over r, and then I'd substitute that in, and then the r's cancel out, right? So they're equivalent to each other. I added a new variable. Let's add that little r, just to keep it consistent there. In this case, again, they gave us velocities, so it's easier to use velocities. Okay, we're out of time, but we'll substitute. Well, let's finish this one up. Let's at least do that. This is going to be negative 36 squared over the radius of this guy, 1250. And I didn't calculate that out, but I'll do that next time. That's where I'll take off. So I'm going to finish this example on on a recording, and I'll post that on there so you can have one more example. There is recitation tonight. We're going to be doing more of these things, right? And then homework's due on Friday. We'll have regular scheduled class on Friday where we're going to start getting into kinetics. So you need the next set of notes by Friday. So print out the next set of notes by this Friday, and then Monday we will not have class. I'll have a recorded lecture. Cool. Break.